Are you laughing?
Hello.
Hello. Why are you giving like Unk energy right now?
Welcome to my lab report on the physics of free-falling objects. Today we will investigate the motion of an object falling straight down from rest, comparing observational data with two computational models, one considering only gravity and the another factoring in both gravity and drag. Our goal is to understand how these forces affect motion and how accurately our models predict reality. The purpose of this lab is to analyze the motion of a falling object and compare the observed position versus time data with predictions from two computational models. The key physics principle applied here is Newton's second law, which states that the force on an object is equal to its mass times acceleration. In the first model, gravity is the only force acting on the object. In the second model, we add a drag force proportional to the square of the object's speed opposing its motion. This represents turbulent drag. Here's a preview of our results. This gravity-only model, which you'll see next, predicts increasing velocity indefinitely, while the drag model also predicts increasing velocity until a terminal velocity. So our system is the crumpled piece of paper. The surroundings is the floor, the air, and the gravitational field exerted by the Earth, and our interactions are gravity, air resistance, or drag, and normal force. The initial conditions are that we start from rest at 2 meters high, and there's a crumpled piece of paper dropped from this height as well. So here is a video. Nice. As you can see, the paper fell. So here's our observed position versus time graph. As you can see, there's many red dots indicating the observed data, and it shows the object's position and velocity over time. And there's a curve in the graph. Here's my two computational models. The first one includes drag. The model assumes zero net force, resulting in constant velocity. And as you can see from the comparison, the model with drag matches the real data more closely. And this slide. Here's the code from GlowScript that allowed for this simulation. So now we see the predicted versus the observed model of force. So the drag force we modeled is proportional to the square of the object's speed. As speed increases, the drag force grows, opposing the gravitational pull. Over time, drag balances gravity, resulting in terminal velocity. And the gravity-only model predicts continuous acceleration, but this doesn't match observed behavior. So now let's talk about terminal velocity. So terminal velocity occurs when drag force equals the gravitational force, leading to zero net force and hence no further acceleration. In our gravity plus drag model, we can also see that the velocity approaches a steady value, confirming this concept. What if we threw the object downwards instead? So an object thrown down initially has a higher velocity, but terminal velocity remains the same, but it's also reached faster because you're going down faster. And the balance between drag and gravity still determines the terminal velocity. So that's what if that happens. So in the conclusion, this experiment demonstrates how well computational models can predict the behavior of real-world systems, especially when drag is included. The gravity-only model falls short in capturing the real behavior of a falling object, while the gravity plus drag model provides a much more accurate prediction. This understanding is crucial for various practical applications from engineering to physics. Here's some possible sources of error. Number one, potential errors include tracking data in the video. Number two, the model assumes turbulent flow, which might not perfectly match the object's motion. And number three, you calibrate the tracking software incorrectly. And there's also frame rate limitations, which I experienced. Thanks. And here's a drawing of Albert Einstein throwing a ball.